Okay, so now you can share.
Okay, very good. So, time to start this EcoDep. Very happy to be here. I'm in the complete jet lag, so I won't make a long speech. I don't even know what this is the first time I have a contact with EcoDep. I'm very happy to be there because I'm a very good friend of Paul, and I'm sure we'll have a very active day. And our first speaker will be Iksanov from Kyiv. We'll talk about the nested Carlin schemes.
Thank you. So thank you very much, Alexander. And that's a real pity that you couldn't attend physically, but I hope next time you can. Or maybe, or maybe we can try something there. Hopefully. Okay.
So should I start?
Yes, I think it's okay. We are more or less at the right time. It's a bit early. Okay, no, but let's go. Yes, okay.
Yeah, okay. Okay, hello everybody, and using this opportunity, I'd like to say a few words about the war. And I'm proud of being Ukrainian. For more than a year, Ukraine is fighting against the major evil of this century, and its name is Russian Federation. We owe the huge debt to the Ukrainian army, which doesn't only protect Ukraine, but also the whole Europe. And most of common Ukrainians work for the victory by either providing generous donation for the army or working as volunteers. And also, we are thankful for the help to all our foreign friends, both at the level of countries and governments and at the level of common people. I don't think that scientists all over the world may stay neutral, and we express a deep gratitude to all who have already raised their voices against the war, and we are waiting at our side all the people who are still hesitating. Okay, and now I'm passing to the scientific part. My talk is based on a recent joint work with Zakhar Kabluchka from Münster and the master student of our department in Kyiv, Valeria Kotelnikova. Nested occupancy schemes in random environment has been my favorite topic since 2017 and still continues to be. However, today I'll be talking on a variation of this model in which the random environment is omitted. And in this way, we arrive at nested Carlin's occupancy scheme. The Carlin occupancy scheme contains infinitely many boxes and some collection of balls. Also, there is a rule of how the balls are distributed over the boxes. The nested Carlin occupancy scheme is comprised of a tree in which each level contains its own infinite array of boxes and again some collection of balls which are the same for all levels of the tree. Also, there is a rule which specifies how the balls are spread over the tree. In particular, this rule makes the scheme nested. I start by giving the definition of classical Carlin occupancy scheme, both deterministic and personalized. Then I discuss some relevant literature, and once this is done, I'll introduce nested Carlin's occupancy scheme and present our main results. Okay. In a classical infinite occupancy scheme, also known as Carlin's occupancy scheme, balls are allocated and independently over an infinite array of boxes, 1, 2, 3, and so on, with probability P1 of hitting box 1, P2 of hitting box 2, and so on. Here the probabilities PRs form a discrete probability distribution. Actually, the PRs may be allowed to be non-negative, in which case we require there are infinitely many positive PRs to ensure that there are indeed infinitely many boxes. How does the scheme look dynamically when there are 5 balls, say? Here is a possible realization. The first ball falls into box 100, the second into box 2, the third into box 3, so on, so forth. And after five balls have been thrown, our occupancy scheme looks as follows. So far, it's unclear what the object of investigation. The characteristics of the infinite occupancy scheme with n balls that I'll be focusing on are Kn, the number of occupied boxes, that is the number of boxes containing at least one ball out of n, and Kn star of y, the number of boxes containing exactly I balls. The variables Kn star of 1, Kn star of 2, Kn star of y, say, with I fixed, are often called small counts. At our previous picture is 5 balls. The number of occupied boxes K5 is equal to 3. There is one box containing one ball. There are 2 boxes containing 2 balls. And the other small counts are equal to 3. Observe that the variable Kn can be interpreted as the number of distinct values assumed by the sample psi1 through psi_n from distribution of PRs, and the variable Kn star of y is the number of values attained by the sample I times. Indeed, the variable psi_j, say, can be associated with the index of a box hit by the j's ball, and then at the previous picture we can see that the sample psi1 through psi5 twice attains the value 2 and twice attains the value 100, so that K5 star of 2 is indeed equal to 2. And now I'm going to introduce an additional source of randomness into the Carlin scheme and discuss the corresponding reward. To this end, denote by pi of t a Poisson process on the non-negative half-line of unit intensity, which is independent of the Carlin scheme. And let also S1, S2, and so on denote its arrival time, so that pi of t as t varies is a counting process for the sequence Sk. There is another version of Carlin scheme called Poissonized. In it, the first ball is thrown at time S1, the second ball at time S2, and so on. As a result, there are pi of t balls thrown at time t. There was no intrinsic time in the original deterministic version with n balls. However, we can artificially introduce time by saying that the case ball is thrown at time k. And what's the motivation behind introducing the Poissonized version? To answer this question, denote by pi k of t the number of balls which fall into the box k in the Poissonized scheme, so that the whole Poisson process pi of t is the sum of pi k of t. And by the thinning property of Poisson processes, the processes pi1, pi2, and so on are independent, and pi k is a Poisson process of intensity pk, where the pk is a hidden probability of box k. Thus, the Poissonized version is more tractable than the deterministic version. Indeed, the numbers of balls falling into different boxes are independent in the Poissonized version, whereas it's not the case in the deterministic version. In particular, the number of occupied boxes is the sum of independent indicators in the Poissonized version and the sum of dependent indicators in the deterministic version. And this explains a common approach used in most of the papers dealing with deterministic scheme. At the first step, the scheme is personalized, that is, deterministic number of balls n is replaced with pi of t, where pi of t is a Poisson random variable. And then the problem at hand is solved for the Poissonized version. And at the very last step, the Poissonized scheme is depersonalized, that is, transfer is made of the results obtained for the Poissonized scheme to the original deterministic scheme. And to close the discussion of the classical Carlin occupancy scheme, I now give some pointers to relevant literature. The scheme was investigated by many authors. Here is an incomplete list of contributors. The picture up to 2007 was surveyed by Gnedin, Hansen, and Pittman. And the last very recent articles, including 2 hours papers published in 2022, which are not given here, indicate that the subject is alive and well. The classical infinite occupancy scheme is usually called Carlin's occupancy scheme because of Carlin's seminal contribution in 1967. The problem of distributional convergence, of one-dimensional distributional convergence of Kn, the number of occupied boxes, was solved by Dudko in 1989, the work of Carlin being an important precursor. Dudko has proved that Kn normalized, centered with its mean and normalized by the standard deviation satisfies a one-dimensional central limit theorem if and only if the variance of the number of occupied boxes diverges to infinity. Chibunin and Kovalevsky proved a functional version of Dudko result. Here it's assumed that the heating probabilities pk are regularly varying at infinity of some index from the open interval -1, 0. The number of balls thrown is n times t, and only n is then sent to infinity, and the scaling limit turns out to be a self-similar Gaussian process. Although a functional limit theorem for small counts wasn't stated in the paper by Chibunin and Kovalevsky, it can be derived from the results. Some other functional limit theorems of similar flavor, still under the regular variation assumption imposed on the hidden probabilities pk, were obtained by Duro and Wong, Duro, Samorodnitsky, Wong, and Chibunin, Zuev. And now I'm going to introduce a nested sequence of Carlin's occupancy schemes, or just nested Carlin's occupancy scheme. Imagine a population of individuals initiated by the single ancestor located in zero generation. It's assumed that a weight is assigned to each individual of the population, and the weight of the initial ancestor is 1. She produces an infinite number of offspring residing in the first generation, and the weights of the first generation individuals are given by hidden probabilities. In particular, the weight of the first child is P1, the weight of the second child is P2, and so on. Observe that we don't assume that the probabilities pk are monotone. Interpreting now individuals of the first generation as boxes and throwing some balls into boxes with probability pk of hidden box k, we obtain Carlin's occupancy scheme with probabilities pk. And what about the second generation? An individual k1 of the first generation, whose weight is P with subindex k1, produces an infinite number of offspring residing in the second generation. For instance, we can think of this individual who produces infinite number of offspring. And the offspring of the individual K1 are enumerated by K11, K12, and so on. And the weights of the offspring are given by the products pk1 times p1, pk1 times p2, and so on by definition. And the other individuals of the first generation act analogously. And the most important thing is that the actions are independent. And it follows from this calculation that the weights of the second generation individuals sum up to 1, and as such can be interpreted as probabilities. So the weights of the second generation individuals form the following discrete probability distribution. And now, for the time being, let's forget about the first generation and interpreting individuals of the second generation as boxes and throwing some balls into the boxes with probability pk1, k2 of hitting box k1, k2, we obtain Carlin's occupancy scheme in the second generation. And the subsequent evolution of the process is similar. The most importantly, all individuals reproduce independently of each other. This is called branching property. And the weight of the case child of some individual is equal to pk times the individual's weight. People familiar with weighted branching processes have already noticed that the tree appearing here is nothing else but a tree of a weighted branching process with deterministic weights. This is rather unusual because normally the weights of a weighted branching process are random. So far, we have only talked about Carlin's occupancy schemes in each generation. And now I want to define a nested sequence of Carlin's occupancy schemes. This means that I have to specify how a particular ball moves from one generation to the next one. And here is the construction. At time 0, infinitely many balls are collected in the root associated with the initial ancestor. And for positive integer n at time n in the deterministic scheme or the time Sn in the personalized scheme, one of the balls collected in the root arrives and falls independently of all the balls that have arrived earlier into the box K1 of the first generation with probability pk1, and simultaneously into the box K1, K2 of the second generation with probability pk2, into the box K1, K2, K3 of the third generation with probability pk3, and so on indefinitely. And the box is deemed occupied, provided it was hit by a ball on its way over the generations. And thus, at the given time, one and the same ball is located in each generation. This is because of this word simultaneously. And this is impossible from the viewpoint of physics, but allowable from the viewpoint of mathematics. Of course, to make the scheme physically acceptable, we could have replaced a ball with its copy whenever a ball moves to the next generation. But I think that mathematically this leads to a complication rather than a simplification. As far as I know, Carlin's occupancy schemes, nested Carlin's occupancy schemes haven't been investigated prior to our work. On the other hand, there is a closely related model which have received more attention. I'm talking about nested occupancy schemes in a random environment. This scheme is very similar to Carlin's occupancy scheme. The only difference is that probabilities pk are now random rather than deterministic. and balls are allocated over the boxes conditionally given the probabilities. The nested occupancy scheme in random environments was introduced by Jean Bertoine in 2008 and further investigated by Joseph Buzinger, Gnedin, Burachevsky, Davgay, Marinovich, Samoilenko, Malan, and myself. The allocation of balls in occupancy scheme in random environment is driven by both randomness of sampling, that is the only randomness which is present in Carlin occupancy scheme, and randomness of probabilities. On the other hand, it is known that typically the behavior of occupancy scheme in random environment is only affected by randomness of probabilities, whereas influence of sampling is not seen. In a sharp contrast, the Carlin occupancy scheme is only driven by randomness of sampling, or there is no other randomness here. So summarizing, the Carlin scheme and the occupancy scheme in random environment should exhibit very different properties, and in most cases, this is indeed true. And now I am passing to the discussion of our main results. And to this end, I need to introduce some additional notation. So PK denotes our basic district probability distribution. And now I denote by rho the counting function of the sequence 1 over PK. If the sequence of PKs is monotone, then rho is just a generalized inverse function for the sequence 1 over PK. Since we don't assume that the probabilities are monotone, the function rho can be thought of as a kind of generalized inverse function for 1 over pk. Now for positive integer j and n, denoted by k and j, the number of occupied boxes in the j generation, provided that n balls have been thrown. And I assume that the number of balls thrown is e to the power t capital plus u, as u and u ranges over the whole real line. Further, I center this random variable with its expectation and normalize with square root of its variance. And here is our first main result. We assume that the counting function rho of the sequence 1 over pk satisfies condition 1 for some non-negative beta and some L slowly varying at infinity. And the claim is that the vector valued process on the left-hand side formed by the numbers of occupied boxes in the subsequent generations converge weakly in the product Skorokhod space. The limit process for one generation, that is just for one coordinate, is a centered stationary Gaussian process with covariance given by formula 2. Furthermore, for different generations, these processes are independent and identically distributed. Thus, what we see here is that nestedness doesn't induce any dependence of generations in the limit. Even though the numbers of occupied boxes in the first generation and in the 10th generation, say, are strongly dependent, they become independent in the limit. And now a few remarks are in order. The denominator in formula 1 is a slowly varying function. I recall that the Dehaene class, usually denoted by pi capital, is a class of functions satisfying relation 1 with arbitrary slowly varying denominator rather than particular denominator given here. So from this, we conclude that the counting function satisfying condition 1 belongs to the Dehaene class phi. Further, it's known that the Dehaene class is a subclass, is a proper subclass of the class of slowly varying functions. So summarizing, the counting function rho satisfying condition 1 is slowly varying at infinity. And referring back to my short survey of relevant literature, I recall that all the writers, or all the previous writers dealing with functional limit theorems for the number of occupied boxes assumed that the heating probabilities are regularly varying at infinity of some index from the open interval minus 1, 0, or equivalently that the counting function rho is regularly varying at infinity of some index from the open interval 0, 1. According to our assumption, as I just explained, the counting function rho is slowly varying, that is regularly varying of index 0. So our result is new even just for the Carlin schemes, that if we restrict our attention to just first generation, say. A natural question is, what is the range of applicability of our theorem, that is, which probability distributions pk satisfy condition 1 and which don't satisfy? We provided in our article sufficient conditions ensuring that the given probability distribution satisfies condition 1. On the one hand, these sufficient conditions are close to necessary, and on the other hand, these are too technical to be presented here. And in view of this, I prefer to discuss this point informally. So let pk be the discrete variable distribution given by the product of C capital times this exponent. Here C is a normalizing constant, ensuring that the probabilities pk sum up to 1. Now, by direct calculation, we can show that the counting function rho is given by the integer part of this logarithm to the power 1 over alpha. The presence of the integer part is not an issue whenever alpha belongs to the open interval 0, 1. In this case, relation 1 holds with beta equal to 1 over alpha minus 1, which is positive, and a slowly varying function L being a constant. Thus, everything is fine, and whenever alpha belongs to this interval, the discrete variable distribution satisfies relation 1. Assume now that alpha is equal to 1, in which case pk is a geometric distribution, and the counting function rho is given by this integer part. And now yes?
No, that was just coughing.
Okay. Okay, and with this choice of rho, the numerator in formula 1 is a bounded function which doesn't converge because of the presence of integer part. Furthermore, when divided by anything divergent to infinity, this ratio goes to 0, and we conclude that relation 1 doesn't hold for geometric distribution. Indeed, if it were, then the parameter beta here would be 0, and according to our assumption, the denominator had to be divergent. However, this is not the case, because if we divide the numerator by anything divergent, we obtain 0 in the limit rather than the logarithm of lambda. The issue with geometric distribution is not a weakness of our theory. The following fact belongs to the folklore. If pk is a geometric distribution, then the number of occupied boxes kn minus its expectation forms a tight sequence which doesn't converge in distribution. More precisely, there are various subsequences along which one obtains different distributional Gumby-like limits. And we conjecture that such a situation persists whenever the tail of underlying distribution pk is not heavier than geometric tail, for instance, Poisson tail. However, as far as I know, this has never been explored so far. So this conjecture, as of today, this conjecture remains open. For positive integer j, denoted by rho j, the counting function of 1 over probability, so 1 over weights in the jth level. Then the counting function rho introduced earlier is just rho1. Now one can show that the counting function rho j is the jth-fold Mellin-Stiltjes convolution of rho with itself. This particularly means that rho j is defined recursively by the following formula. For the proof of our theorem, one has to ensure that the counting function rho j inherits the assumed property of the counting function rho to belong to the Dehaene class phi. However, we don't know whether the fact that the given function belongs to the Dehaene class implies that its Mellin-Stiltjes convolutions belong to the Dehaene class phi. And this seems to be an interesting open analytic problem. And so this, our additional assumption about the particular form of denominator in Formula 1 enables us to prove that the following limit relation holds. And since the denominator here is again a slowly varying function, we conclude that indeed the function rho j does belong to the Dehaene class as desired. However, I'd like to stress that this assumption about particular form of the denominator is only used for this lemma. So this is the only place in our paper where this specific form is needed. In particular, the stated functional limit theorem for the number of occupied boxes holds for the first level, and is the sole assumption that the counting function rho belongs to the Dehaene class pi without specification of denominator in Formula 1. That is, we can, as far as the first generation is concerned, we can put here any slowly varying function divergent to infinity. So in particular, this specific form is not needed. And now I'd like to discuss briefly the idea of proof. The proof consists of several steps. And at the first step, we replace deterministic number of balls with pi of t balls. I recall that pi of t is a Poisson process of unit intensity, which is independent of sampling. And as I have already noticed, have already mentioned, the advantage of this is that the Poissonized number of occupied boxes is the sum of independent indicators. Here, each indicator corresponds to one box, and the process appearing here, pi with subindices k1 through kj, is a Poisson process of intensity with intensity being the heating probability of the box K1 up to Kj. And furthermore, for different boxes of the J generation, these Poisson processes are independent, and the latter fact follows from the same property of Poisson processes. So summarizing, here we have an infinite sum of independent indicators. As usual, the proof of a functional limit theorem consists of proving weak convergence of finite dimensional distributions and then tightness. While proving weak convergence of finite dimensional distributions in the present context, that is this limit relation, we exploit the Kramer-Wald device. This enables us to work with linear combinations instead of vectors. And now, with some additional efforts, one can show that the written here linear combination is an infinite sum of centered independent random variables with finite second moments. Hence, the Lindeberg-Feller central limit theorem applies and yields the claimed weak convergence of finite dimensional distributions as well as independence of the coordinates of the limit Gaussian process. To prove tightness, we use standard sufficient conditions for tightness in the Skorokhod space borrowed from Billingsley's book. These deal with mixed moments of two increments, and in our particular setting, take the following form. The most important thing to obtain uniform bound, which doesn't depend on T capital. And finally, at the last step, we have to get back to original deterministic setting with n goals, and this requires some additional technical work, the main technical tool being the continuous mapping theorem. Many Gaussian processes appearing as weak limits or scaling limits admit integral representations. Perhaps the simplest instance is the Skorokhod integral, in which the integrand is a deterministic function like the power or the exponent, and the integrator is a standard Brownian motion. Such integral representations are very useful for simulation purposes and provide nice pathwise descriptions of the limit Gaussian processes. In view of the simple form of covariance in our limit theorem, we became curious whether an integral representation of our limit process is possible. And our findings are presented in the next result. It turns out that an integral representation with respect to a two-dimensional Gaussian white noise is possible. The integrand here is deterministic function. And from this integral representation, it's immediate that the process Z given by this integral is a stationary centered Gaussian process. There is a simple formula for the covariance of the integral with respect to the Gaussian white noise, and using this formula, it's a few lines computation to show that the so-defined process Z have variance of this form, and which is the same as in our first result. And finally, the very last claim about further continuity follows from the Kolmogorov-Chentsov theorem. And to apply the theorem, the integral representation is not needed. the explicit form of covariance suffices. And finally, I present a result about occupancy profile, or in other words, a result about the weak asymptotic behavior of small counts in nested Carlin's occupancy scheme. The assumption here is the same as in our previous theorem. So we assume that the counting function rho satisfies this limit relation, which particularly means that rho belongs to the Dehan class. The theorem is hard to read because of too many indices. So let me explain what is this. So this random variable is the number of J's generation boxes which contain exactly L balls, provided that e to the power t capital plus u balls have been thrown. And the claim is that the matrix valued process on the left-hand side converge weakly to some matrix valued process. The jth row of the matrix on the left-hand side may be called occupancy profile of the jth generation, and it's given by occupancy count, by small counts properly normalized and centered within the jth generation. And what's the limit? It turns out that the rows of the limit matrix are independent and identically distributed. The limit processes within one row are dependent, centered stationary Gaussian processes, and each particular process admits the following integral representation. Here, W2, W3, and so on form a sequence of consistent finite dimensional Gaussian white noises. And all of these are obtained as a restriction of the parent infinite dimensional Gaussian white noise, with intensity being the product of the Lebesgue measure on the real line times the distribution of an infinite sequence of independent random variables having a uniform distribution on 0, 1. In particular, the dependence of the processes xy and xj, say, is captured by the dependence of the corresponding Gaussian white noises wi plus 1 and wj plus 1, say. Also, we have an explicit formula for the covariance of the limit process. And of course, since the limit process is stationary, the covariance only depends on the absolute value of the difference of arguments. And finally, there is, I think, not too complicated explicit formula for the cross covariances of the limit processes XL1 and XL2. I recall that XL1 is the limit process for the number of boxes containing L1 balls, and XL2 is the limit process for the number of boxes containing L2 boxes. Okay, and I stop here and thank you for your attention, and Slava Ukraini.
Are there questions or comments? Please let us.
My question would be, is there a continuous version of Carlin's scheme where very small balls are thrown at each point, so that according to a continuous distribution with continuous argument?
Thank you for the question. This perfectly makes sense, and it would be very interesting to consider. But as far as I know, such a scheme hasn't been investigated so far. But you are right, it may be very interesting to look at this continuous type version of Carlin scheme. At least I don't know. I have never seen these kinds of results for continuous type version.
That's another. Your main results concern the Carlin scheme with deterministic probability.
Yes.
And are there similar results for random probabilities?
Yeah, of course. There are numerous results by our group, by Jean Bertvan. I have given a list of corresponding publications, but I wasn't able to put all these results into one talk, so I decided to concentrate on just the discrete deterministic probabilities. But yeah, we obtained many results for the Carlin scheme with random probabilities. If I'm able, just a moment. There are some results about almost sure convergence in the original Bertvan paper. And for instance, the last 4 papers are dealing with exactly functional limit theorems for occupancy schemes with random probabilities in various settings under various assumptions. And yeah. But I wasn't able to present this result within one talk.
I understood at some point that you said that the results in random environment are really different from the one when you fix the environment. How could that be?
Once again, the very last words I didn't hear.
From your own talk, I thought I understood that you said that the results in random environment that you're presenting here are in fact different from the one with a fixed distribution.
No, these results, the results. So in my talk, I presented results for fixed environment. That is for when the probabilities are deterministic. There is another group of results dealing with random probabilities, but in their nature, these two groups of results are absolutely different. And I would say they are not comparable. Well, once again, why is that? Because as far as deterministic probabilities are concerned, then the behavior of the scheme is only driven by randomness of sampling, that is, randomness of how you distribute boxes. If you consider occupancy scheme in random environment, that is with random probabilities, then everything is driven by randomness of only probabilities, whereas the influence of randomness of sampling is not seen at all. That's what, so these two occupancy schemes are driven by absolutely different sources.
Thank you.
Yeah.
Are there other questions or yes, please?
It's not a question, it's not a comment, it's just taking the opportunity to meet Alexander Iksanov almost face to face. And I would like to tell you that his paper, joined with Andrei Filipenko, got Ito Prize for the best paper published in stochastic processes and applications in years 21, 22. And I take the opportunity to congratulate Alexander.
Yeah. Thank you very much. Thank you very much. It's a great pleasure and great honor. Thank you.
So we thank you again, and maybe we will just have a little break and have some coffee. And so unfortunately you cannot come with us, but okay, thank you again.
Yeah, thank you. Thank you.
I will close the Zoom and I will reopen it later.